Hi, my name is Jonathan. I'm a sophomore physics student from Spring, Texas, and I participate in the magnetic matter stream. Our lab is concerned with condensed matter physics, which is the study of the properties of all sorts of exotic materials. Come on inside. I've got some really cool things to show you. In our lab, I get to work on building our understanding of superconductors. A particular material is said to be a superconductor when, under the right conditions, it is able to carry electricity really far without losing any electrical energy along the way. Besides just being cool, superconductors are worth studying because the efficiency with which they carry electricity makes them potentially super useful for things like quantum computing and power distribution. Understanding what causes a material to superconduct is a really big deal because so far the only superconductors known to exist only act as superconductors at really cold temperatures, think negative 450 degrees Fahrenheit, and or at ridiculously high pressures, which makes them pretty hard to use in any practical application. But figuring out what makes a material superconduct would help us look for materials that exhibit superconductivity near room temperature and atmospheric pressure. That's the hope anyways. Superconductors based on copper and other similar superconducting materials that work at the comparatively much higher temperature of liquid nitrogen have been well studied since their discovery in 1986. But not a whole lot of progress in finding other classes of superconductors have been made until 2019, when a group at Stanford University discovered nickel-based superconductors. There's lots to be learned about this new class of superconductors, and I can't even begin to tell you how exciting it is to be involved in such new science as a college student. My project is all about the properties of these new nickel-like superconductors when we make them into super thin layer on a ceramic chip like this. To make the thin layer, or film, of superconductor, we use the laser behind me to vaporize pieces of a chunk of superconducting material. The laser essentially splashes that material onto the ceramic chip, creating the thin film. It's kind of like how doing cannonball into a pool will splash water onto the pool deck and wet it. What we were really interested in knowing about the thin film is how well it conducts electricity at different temperatures. To figure that out, we measure the thin film's resistance using this intricate machine that sucks all the air out from around the sample and zaps the sample with electricity as it lowers the temperature to 450 degrees Fahrenheit below zero. Zapping the sample while it's inside of this ultra-powerful electromagnet tells us some important information on how the electricity flows through the sample. These have just been the major aspects to my project. Along the way, I also get to stick things in this 1000 degrees Celsius oven. I also get to use this fancy microscope, called an atomic force microscope, to measure the surface structure of the ceramic chip before we put the thin film on it in the first place. What's really cool about this machine is that the part that does the actual picture taking, this thing, is a spike so sharp that it comes to a single atom at its tip. It sure has been a lot of fun taking part in the magnetic matter stream. What I enjoy most of all is the supporting and fun environment that my lab mates, the graduate students, and Dr. Margaret have all cultivated here. We really have a great time, and I sincerely hope that you'll consider us when it comes time for stream sort. Until then, take care, friends.